The minimum circuit ampacity rating indicates the minimum allowable amperage for the circuit that supplies the machine. In this case, the minimum circuit ampacity is 28 amps for side 2. As a general rule, the circuit ampacity should be equal to or greater than the minimum circuit ampacity. The maximum fuse rating indicates the maximum allowable amperage for the fuse or circuit breaker that protects the circuit. In this case, the maximum fuse rating is 35 amps for side 2. You want to avoid using a fuse or circuit breaker with a rating higher than the maximum fuse rating, as this can create a fire hazard. Therefore, a 30 amps breaker would be sufficient for side 2, assuming you use a 10 American wire gauge wire that has an ampacity of 30 amps. The fact that the coffee maker has a 30 amps dryer plug does not necessarily mean that it draws 30 amps continuously. A coffee maker's ampacity will depend on its specific design and usage patterns. In this case, the coffee maker draws 25.8 amps. Since the coffee maker is not likely to operate continuously, a 30 amps breaker and receptacle should be sufficient to handle its load. Therefore, use a 30 amps breaker and 10 American wire gauge wire for side 2 of the ice cream machine, and use a 30 amps breaker and receptacle for the coffee maker. Now let's delve deeper into the concept of minimum circuit ampacity and its significance in electrical installations. The minimum circuit ampacity, often abbreviated as MCA, is a crucial parameter that dictates the minimum current carrying capacity required for a circuit to safely and effectively power a specific piece of equipment or appliance. It is typically specified by the manufacturer of the equipment and is based on the anticipated load that the equipment will draw under normal operating conditions. Understanding and adhering to the MCA is paramount for several reasons. Firstly, it ensures the safe operation of the equipment. Using a circuit with an ampacity lower than the MCA can lead to overheating of the wires, which can potentially cause insulation damage, electrical fires, and equipment failure. Secondly, it guarantees the reliable performance of the equipment. If the circuit cannot supply the required current, the equipment may experience voltage drops, reduced performance, or even complete malfunction. Thirdly, it complies with electrical codes and regulations. Electrical codes, such as the National Electrical Code, or NEC, mandate that electrical installations meet certain safety standards, including the proper sizing of circuits based on the MCA of the connected equipment. Now let's explore the factors that influence the MCA of an electrical appliance or equipment. The MCA is primarily determined by the power consumption of the equipment, which is typically expressed in watts or volt amps. The higher the power consumption, the greater the current draw, and consequently the higher the MCA. Other factors that can affect the MCA include the equipment's operating cycle, duty cycle, and any surge currents that may occur during startup or operation. It is important to consult the equipment's nameplate or technical documentation to obtain the accurate MCA value. When selecting the appropriate wire size and overcurrent protection device, such as a circuit breaker or fuse, for a circuit, it is essential to consider the MCA. The wire size must be sufficient to handle the MCA without overheating, and the overcurrent protection device must be sized to protect the circuit from overloads and short circuits while allowing the equipment to operate normally. NEC provides guidelines and tables for determining the appropriate wire size and overcurrent protection device based on the MCA and other factors. Now, let's elaborate on the significance of the maximum fuse rating, often referred to as the MFR. The maximum fuse rating is the highest permissible amperage rating for the overcurrent protection device, such as a fuse or circuit breaker, that protects the electrical circuit supplying the equipment. This rating is established by the equipment manufacturer to safeguard the equipment and the electrical system from potential damage caused by excessive current flow. The MFR acts as a critical safety barrier, preventing the use of overcurrent protection devices that could potentially allow dangerously high currents to flow through the circuit. Exceeding the MFR can lead to severe consequences, including equipment damage, electrical fires, and even personal injury. The primary purpose of the MFR is to ensure that the overcurrent protection device will effectively interrupt the circuit in the event of an overload or short circuit. An overload occurs when the current flow exceeds the normal operating current of the equipment, while a short circuit occurs when there is an unintended low resistance path for current to flow, resulting in a rapid and substantial increase in current. If the overcurrent protection device has a rating higher than the MFR, it may not trip or blow quickly enough to prevent damage to the equipment or the electrical system. This can lead to overheating of wires, insulation breakdown, and potentially a fire. The MFR is typically marked on the equipment's nameplate or in its technical documentation. It is crucial to adhere to this rating when selecting and installing the overcurrent protection device. Using a fuse or circuit breaker with a rating lower than the MFR is generally acceptable, as it will provide a higher level of protection. However, it is important to ensure that the overcurrent protection device is still adequately sized to handle the normal operating current of the equipment without nuisance tripping. Nuisance tripping refers to the unwanted tripping of the overcurrent protection device due to temporary current surges or fluctuations that are within the equipment's normal operating range. In summary, the maximum fuse rating is a critical safety parameter that must be strictly adhered to when installing and maintaining electrical equipment. It ensures that the overcurrent protection device will effectively protect the equipment and the electrical system from overloads and short circuits, preventing potential damage and hazard. Now let's discuss the selection of appropriate wire gauge and its relevance to the circuit's ampacity. The wire gauge, typically expressed in American wire gauge, or AUG, is a numerical representation of the wire's diameter. The smaller the AWG number, the larger the wire's diameter, and consequently, the higher its current carrying capacity, also known as ampacity. Selecting the appropriate wire gauge for an electrical circuit is of paramount importance to ensure safe and reliable operation. Using a wire gauge that is too small for the intended current can lead to several problems, including overheating, voltage drops, and potential fire hazards. The ampacity of a wire is determined by several factors, including the wire's material, insulation type, and the ambient temperature in which it is installed. Copper wires generally have a higher ampacity than aluminum wires due to their superior conductivity. Different insulation types have different temperature ratings which affect the wire's ability to dissipate heat. Higher ambient temperatures can reduce the wire's ampacity, as the wire's insulation may degrade at elevated temperatures. The NEC provides tables that specify the ampacity of different wire gauges based on their material, insulation type, and ambient temperature. These tables are essential for selecting the appropriate wire gauge for a given application. When selecting a wire gauge, it is crucial to consider the circuit's ampacity, which is the maximum current that the circuit is expected to carry. The wire gauge must be selected such that its ampacity is equal to or greater than the circuit's ampacity. In addition to the circuit's ampacity, it is also important to consider the voltage drop in the circuit. Voltage drop is the reduction in voltage that occurs along the length of the wire due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting the voltage drop in branch circuits to 3% and in feeders to 5%. To minimize voltage drop, it may be necessary to use a larger wire gauge than would be required based solely on the circuit's ampacity. In summary, selecting the appropriate wire gauge is a critical step in electrical installations. The wire gauge must be selected such that its ampacity is sufficient to handle the circuit's current, and the voltage drop is within acceptable limits. The NEC provides valuable guidance and tables for determining the appropriate wire gauge for various applications. Now let's focus on the importance of continuous load considerations when sizing electrical circuits and overcurrent protection. A continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. When sizing electrical circuits and overcurrent protection devices for continuous loads, it is crucial to account for the sustained current draw to prevent overheating and ensure reliable operation. The NEC mandates specific requirements for sizing circuits and overcurrent protection devices for continuous loads. These requirements are designed to provide an additional margin of safety to account for the prolonged heat buildup that can occur when a circuit is continuously loaded. For continuous loads, the overcurrent protection device, such as a circuit breaker or fuse, must be rated at not less than 125% of the continuous load current. This means that if a circuit is expected to carry a continuous load of 20 amps, the overcurrent protection device must be rated at least 25 amps. Similarly, the conductors, or wires supplying a continuous load, must be sized to carry not less than 125% of the continuous load current. This ensures that the wires will not overheat when subjected to the sustained current draw. The 125% factor is applied to both the overcurrent protection device and the conductors to provide a coordinated protection scheme. This ensures that the overcurrent protection device will trip or blow before the conductors are subjected to excessive heat. Determining whether a load is continuous or non-continuous can sometimes be subjective. However, as a general guideline, if a load is expected to operate at its maximum current draw for 3 hours or more, it should be considered a continuous load. Examples of continuous loads include electric heating systems, air conditioning systems, and some types of lighting. In contrast, loads that operate intermittently or for short durations are considered non-continuous loads. Examples of non-continuous loads include appliances such as coffee makers, toasters, and hair dryers. In summary, when sizing electrical circuits and overcurrent protection devices for continuous loads, it is essential to apply the 125% factor to both the overcurrent protection device and the conductors. This ensures that the circuit will be able to handle the sustained current draw without overheating, and that the overcurrent protection device will provide adequate protection. Now, let's address the voltage considerations when dealing with electrical equipment designed for specific voltage ranges. Electrical equipment is often designed to operate within a specific voltage range, such as 208 volts to 230 volts. This range indicates the acceptable voltage levels at which the equipment can function safely and efficiently. When the available voltage falls within the equipment's specified voltage range, the equipment should operate normally without any issues. However, when the available voltage falls outside the specified range, it can lead to various problems, including reduced performance, equipment damage, or even safety hazards. In cases where the available voltage is higher than the equipment's maximum voltage rating, it can lead to overvoltage conditions. Overvoltage can stress the equipment's internal components, potentially causing premature failure or damage. It can also increase the risk of electrical arcing and insulation breakdown, which can lead to fires. In cases where the available voltage is lower than the equipment's minimum voltage rating, it can lead to undervoltage conditions. Undervoltage can cause the equipment to operate inefficiently, produce less power, or even fail to start. It can also damage the equipment's motor or other sensitive components. When dealing with equipment that has a specified voltage range, it is essential to ensure that the available voltage falls within that range. This can be accomplished by using a voltmeter to measure the voltage of the equipment's power source. If the available voltage is outside this specified range, it may be necessary to take corrective actions, such as adjusting the voltage at the source, using a voltage regulator, or replacing the equipment with one that is compatible with the available voltage. In situations where the available voltage is close to the equipment's maximum or minimum voltage rating, it is advisable to consult with a qualified electrician to determine the best course of action. An electrician can assess the situation and recommend appropriate solutions to ensure the safe and reliable operation of the equipment. In summary, voltage considerations are crucial when dealing with electrical equipment designed for specific voltage ranges. It is essential to ensure that the available voltage falls within the equipment's specified range to prevent overvoltage or undervoltage conditions, which can lead to equipment damage or safety hazards. Now, let's briefly touch upon the National Electrical Code, or NEC, and its role in ensuring safe electrical installations. The NEC is a comprehensive set of standards and guidelines for electrical installations in the United States. It is developed and maintained by the National Fire Protection Association, or NFPA, and is updated every 3 years to reflect the latest advancements in electrical technology and safety practices. The NEC covers a wide range of topics related to electrical installations, including wiring methods, overcurrent protection, grounding, and equipment installation. It provides detailed requirements for ensuring that electrical systems are installed and maintained in a safe and reliable manner. Compliance with the NEC is often mandated by state and local jurisdictions, and it is essential for all electrical professionals to be familiar with its provisions. The NEC is not a law itself, but it is often adopted into law by various jurisdictions. The NEC is organized into chapters, articles, and sections, each addressing specific aspects of electrical installations. It includes numerous tables and diagrams to aid in understanding and applying its requirements. The NEC is a complex and comprehensive document, and it is not intended to be a substitute for sound engineering judgment. However, it provides a valuable framework for ensuring that electrical installations are performed safely and in accordance with industry best practices. In summary, the NEC is a critical resource for electrical professionals, providing comprehensive standards and guidelines for safe and reliable electrical installations. Compliance with the NEC is often mandated by law and is essential for protecting people and property from electrical hazards. And remember, always consult with a qualified electrician for any electrical work to ensure safety and compliance with local codes.